getting these LiDAR products ready for the community to use, and we'll be covering some examples on that today.
Thank you, HP. Okay, can you hear me? Okay. Yeah. So for this tutorial on LiDAR, the notebook that we'll be using is inside the LiDAR folder. So if you go to the book, tutorial folder, inside LiDAR, there are 3 IPYNB files that we're going to use for this tutorial. So let's get started with the first one, introduction. So I would like to give a quick overview of the objectives of this tutorial. Firstly, I'll begin by introducing us to LiDAR remote sensing. And then from there, we're going to take a look at LiDAR data formats, point cloud, and explore and see what the point cloud looks like. And then we're going to look at the approach for deriving snow product, snow depth, differencing DM. And lastly, and most importantly, we'll talk about some common pitfalls that could arise when we are working with elevation data, when we are differencing elevation. So, LiDAR is an active remote sensing techniques. It works by sending pulses of light, of lasers from the platform down to the surface, and it records the time it takes for the pulses to get back to the detector. So this two-way travel time is converted to range or height, from which you cannot determine or derive the elevation of the surface. LiDAR is very important. Its advantage is that it provides very accurate elevation data at high resolution. In this figure, I am showing a 10-meter pixel resolution DM. And we can see that we can see the undulation of the terrain. We can see the hills and all that, but we couldn't see the fine resolution details like we have in the 1-meter DM. So LiDAR data provides high resolution and very accurate that's where we use it for validation and for analyzing the distributions of snow depth, vegetations across our study area. LiDAR could be classified based on different techniques, but based on the platform, we have 3 types of LiDAR. We have the ground-based LiDAR, or the TLS, terrestrial laser scanning. We have the airborne LiDAR and the spaceborne LiDAR. For this tutorial, I'm going to focus on the airborne LiDAR. So this is a component of airborne LiDAR system. We have the airplane that flies over the study area, and on board the airplane, we have the laser scanner, which emits the laser pulses. And there's also IMU, because as the airplane flies over the study area, it is not stable. There are some rotation and tilting. So we need the IMU to measure the rotation of the airborne in order to determine the correct orientation of the scanner. And also the GPS, which gives the precise location of the scanner as it moves over the study area. We also need ground control points. So this GPS base station provides coordinates of some known points on the ground. So with this, we could derive the elevations of the surface. LiDAR data records 2 types. We could get 2 types of data from LiDAR. The range distance is what from range distance, you can get the elevation. And in addition to the range, we also have intensity, which is like the fractions of the pulses that is returned back. Because for LiDAR, we could have like mostly used scanner is the infrared. So for infrared, over vegetation reflects infrared very high. So you have high reflections. So this intensity, imagine we have like 1 million pulses, and then over vegetation, and we have like 800,000 that is returned back. So this is very high. But over water, there is absorption. So there is going to be a low intensity return. And also, each LiDAR pulse yields multiple returns, depending on the structure of the features that the return is coming from. So the number of returns can be used to characterize the Earth features. So in this diagram, I'm showing a laser pulse that is coming from a vegetation, a tree. And we could see here, we have 4 distinct returns. The first return usually is from the surface of the feature. It could be a bare earth, it could be a building, it could be a vegetation. And we could have some number of returns in between the first and the last. And this complexity of returns can be used to characterize the surface that the return is coming from. So we have canopy structure from analyzing the multiple returns of laser pulses. So most times, elevation data use the first return and the last return, because the first return is going to give the digital surface model, and the last return is usually the bare heads. So I'm showing the distinction between the digital terrain model and the digital surface model in this figure. So digital terrain model is the 3-dimensional representation of the Earth surface without natural or man-made features. So this is representing the bare head elevation. And the digital surface model, which is like the first return of a laser pulse, is including the man-made and natural features. So let's look at what a point cloud entails. So in this activity, I want us to explore this online LiDAR data viewer plus.io. So if we click at this, it's going to take us to this platform where we can view a point cloud. If you have a point cloud of your own, you can import it. But my experience with this platform is that it's very slow to load. Yeah, point clouds are very, very dense. Yeah, they are very overwhelming, large size. So it takes a lot of time to load most of the data that I've tried to explore with it. But for the sake of this tutorial, I want us to explore the preloaded data set. So if you want to load your own point cloud, you could just browse and import it. But I would like us to explore one of the preloaded data here. And I love looking at this Austin Stadium. So if we click on that, it might take a few seconds to load. So we could look at the options that we have, the buttons. We could change the density of the point cloud to increase the speed of visualization and analysis. We can, importantly, change the colorization here. So here, the default colorization is RGB, which is showing the way our visual is going to see the features. But we could change this to classification, which is to show what are the classes of the features that we have in the point cloud. and also heat map, which shows the elevation. It colors the features based on elevation. Yeah, another thing we can show here is the intensity, which is the number intensity of photons that is returned. Yeah, this is taken. Okay. Okay, while that is loading, I would like to move to the next section, which is to talk about how do we go from the point cloud to pixels, because most of us, we want to work with pixels, because the point cloud is very overwhelming for many scientific applications. So we usually work with the pixels that are derived from the point clouds. There are a lot of tools for rasterizing point clouds, but a very important and common open source tool is PDAL, which is Point Data Abstraction Library. So it works in two steps: filtering and rasterization and rasterizing. So the pipelines, I will not talk about the process to move from point cloud to raster, but I will just I put a link here to a post if you want to read more about how to go from point cloud to raster. So let's see if we have this. Yeah. Okay. So this is the point cloud of the Austin Stadium, and we could see how we have a lot of points over the region that give insight of elevations. We can see the stadium, we could see vegetations, we could see the river here. And I mean, over the river, it looks like there is no point cloud, right? This is because this is in most airborne LiDAR use infrared. So like I said, it's a lot of absorption over infrared over water bodies. So there's no point here. I want us to change this to heat map color. Yeah, heat map color, and we see how the point clouds are colored based on the elevation. So you could do a lot of things with this online viewer just to see a perspective of what a point cloud is. They are basically points, a lot of points over the study areas that give perceptions of elevations. So now, after we moved from point cloud to raster, we want to do some analysis, derive some products, right? The primary product from LiDAR are DM and DSM. Now I'm moving to notebook 2, elevation differencing. So here, the goal of this is to show us how do we derive the snow-related product from LiDAR, DM, or elevation data. So here, canopy height is a very popular LiDAR product, but for our application, most of us, we need, in addition to canopy height, the snow depth to validate other remote sensing techniques. So to derive canopy height, we difference the DSM and we subtract the DTM from the DSM. It's a difference of DSM and DTM that gives the canopy height as illustrated in this plot. And for the snow depth, it's just this snow on DM, difference of snow on DM and snow off DM. That gives the snow depth. So we're going to take a look at that. I want us to move a bit forward to the data download step here, because it takes a couple of minutes. I don't know how fast that might be. So let's click this data download to start the downloading of the data while I start talking about the packages that we use. Are we there, everybody? Are we at the download section? Okay. So I think Dylan has done a great job of talking about the packages in his presentation. So here I'm importing the plotting packages, matplotlib, Seaborn, and hvplot for interactive visualization of the elevation data. And here, these are the geospatial packages that I'm using. While the data is downloading, I think I have the data here already downloaded for me. So I'm going to talk about the data we're going to use for the hands-on demonstration. So I'm going to open the terminal. So the data will be downloaded inside the temp directory. So let's see. Oh. What's happening?
Hey, Naheem, can you unmute your mic, my friend?
Okay.
Thank you.
Okay. Yeah, so let's list the content of the temp. So we have the data downloaded and it has been unzipped as input directory. So list what is the inside the input. So these are the files that we have in the input folder. So I have the ASO 3 meter Grand Mesa Sonar DM. I have QSI 0.5 meter resolution winter DEM. So what I want to do show with these two data is how do I derive snow depth from these two DM data. Then I have Cameroon Sonar DM and then Cameroon Sonar DSM. And I have two files, GTF files, GTX file. I'm going to show what we're going to see what I use this for. Then I also have some geopackage, 100 randomly sampled points over Cameroon site. So this is the content of the folder, data folder. So go back to the website, book, tutorial, LiDAR. So continue from this. So let's import the necessary packages. And then after downloading the data, I'm reading the Snow on DM for Cameroon and then the Snow Free DM for Cameroon using RealXarray package. Then to derive the snow depth, just difference this Snow Free DM and the Snow on DM. That will give us the snow depth. And then for the vegetation or the canopy height, we are going to read the DSM. So I'm reading the Snow Free DSM and then difference the DSM and the DEM to get the vegetation height. So let's click that, let's run that. And what does the data array object looks like? Again, Dylan actually talked a lot about this data array, and I don't want to, and in the interest of time, I will just reiterate a few points here. So it's a kind of multi-dimensional labeled array. you consider a NumPy array, but we now have labeling kind of data frame or something like that. So that facilitates indexing and analysis. So it has a lot of values. We have 145 million values for this data because it's high resolution, 0.5 meter. So let's look at some properties of the raster. So the shape, the coordinate reference system, the bands, and the resolution. So the resolution is 0.5. This coordinate reference system is in WKT format, well-known text format. It's not so intuitive. We can look at the EPSG later. Yeah, let's take a quick plot using. Okay, taking some minutes, some seconds. Okay, so this is the snow depth product we derived from differencing the snow on and the snow free DEMs. And this plot gives us an insight into the accuracy of our LiDAR data. And we can see over the road, the snow depth is about 0 over the road. And even the reservoir here, the snow depth is negative. And I mean, we could see how the LiDAR snow depth is very accurate to capture the snow distribution over the study region. So for faster analysis, I'm trying to subset the data over small regions. So here, I'm slicing over this region and then store that as Cameroon DM region of interest, as well as for the vegetation height and the snow depth. And then let's plot what that subset regions looks like. Let's see with matplotlib. So yeah, I'm setting the style for the matplotlib, and then I'm using the plot functions of the data array, and I set the title and all necessary settings. So this is the DEM over the subset region, and this is the vegetation height, and this is the snow depth. So you see that the region we subsetted is mostly vegetation area, except for the road and for the reservoir, where of course there is no vegetation over the road. Yes, and then so we want to do further analysis with the elevation, the vegetation, and then the snow depth raster. Besides using LiDAR data for validation, which is probably what most of us working with other remote sensing techniques will be doing, another application is that you might want to use a product to understand the distributions of snow or vegetation over our study area. So the goal of this next section is for us to see how we can understand distributions of snow and vegetation using the product we have computed in previous sections. So what I'm doing here is that I showed you the data folder, and I have a point feature, 100 randomly sample point over the study area. So I want to perform Sonar statistics over a buffer of 20 meters at each of the points, and then derive the snow depth, extract the mean snow depth over the 20-meter buffer and the mean vegetation height and then elevation, and then look at how each of these variables correlate with one another and are distributed over the region. So here, I am reading the sample point using GeoPandas, and I create a folder here. This line of code is creating a folder, if it doesn't exist, of output, where I'll be storing my results. And then here I create a buffer of 20 meters for each of the points. So let's run that. And then the next one is just plotting the buffered polygon. So we could see how the points are distributed over the subset region. So what I want to do with the next cell is the Sonar statistics analysis. So here, I'm calling the Sonar stats method of raster statistics package. And I'm putting the buffered feature, and the statistics that I want basically is the mean of the pixels that fall within each buffered region. And then this is going to give us a GeoJSON object. And then I am converting that to a geodata frame using geodata frame.from features. And then I rename the columns, the count columns, and then the main column. So I do that for vegetation height and for snow depth, as well as for DEM. So let's run that. So the next cell here is basically doing a couple of plotting. Here I'll start running it. So here I do the styling, set the style and this axis, and then I plot I made a box plot of the snow depth, vegetation and elevation, and also the distribution histogram, and a KDE plot, which is like a scatter plot of snow depth against elevation and snow depth with vegetation. And I mean, based on the plot earlier, we could see that most of the sampled region is over low elevation, lower than below 3,100 meters, and that is, I mean, reflected in the heat plots over here. And also, we see that the snow depth majorly is over high vegetation area, as shown by this KDE plot. So, yeah, this is one of the many applications of LiDAR data in our analysis. I think there are some groups that are working with incorporating LiDAR with some other techniques to improve the estimation of snow parameters. Yes. Where we discuss the common pitfalls in elevation differencing. So the differencing that I did in the previous notebook is basically straightforward. I'm just taking the DEM and the DSM to get the vegetation height, and then for the snow depth, I'm using the snow on and the snow free DEM. Well, at times it might be a bit complicated. It was easy because the data that I've been using for Cameroon data, I have the snow on and the snow free DEM that were acquired by the same source, from the same source, QSI. But in situation where we have elevation data from one source and elevation data from another source, it might take extra effort for us to really make sure that we get accurate results, because you have to take into consideration what is the resolution of each data. Are they the same? What is the coordinate reference system? And then what is the datum that each elevation data is referenced to? So the goal of this section is to make us to see how we can go around these challenges of differences in raster metadata and information from different sources. So yeah, let's run the, so for this demonstration, I have the 3-meter DEM data by ASO over Grand Mesa, and 0.5 meter resolution snow on DEM by QSI. So we don't need to download the data again because it's already downloaded. So the first thing we need to do is to make sure that the data are in the same resolution. So QSI data is in higher resolution, 0.5 meter, ASO is 3 meter. So what I'm doing here is to translate to downsample the QSI data to 3 meter. So I'm using GDAR translate. So run that, take a couple of seconds, and I'm saving that as inside the output directory as QSI 3 meter Grand Mesa winter DEM. So if we look at the information of the raster data, we see now that it is 3 meter. Now pixel size is now 3 meter. So now let's read the DEM, Snow on DEM using our XRA package and plot it. And also move to the next cell. So this is what the DEM, Snow on DEM for Grand Mesa looks like. Then let's read the ASO data and plot. So from here, we can see that these two data, they cover different extents. ASO data cover larger area compared to QSI data. So, I mean, it's just logical that we want to subset, make sure that they are in the same extent and coordinate reference system before we do the differencing. So this next code cell that I'm calling, we project _match.
Question, learning a little more about how you did GDAL translate there versus like calling for the command line in that case, and that's technically not Python. Just to add a little bit more to that step, because I think it's super important.
Yeah.
Command line stuff can get a little bit.
Okay. Yeah. So to use GDAL in notebook as a command line, I use this what's the symbol? Yeah, exclamation mark. Yeah, this exclamation mark before the command. So this we understand that it is a command line stuff. And then here, I'm specifying the option, right? So any slash before any alphabet is like option. Target resolution is 3 meter by 3 meter. And then most of the GDAL commands take input and output, right? So for this GDAL translate, I'm specifying the input to be the 0.5 meter resolution winter DEM, and then I'm saving that the output should be 3 meter to be saved as this, right? Okay. And so yeah, I'm using the project to match to make sure that the snow on DM and the snow free DM are in the same extent and in the same coordinate reference system. So then the next code cell here is the difference in, like we did earlier, to get the snow depth. So what do we have? We have, wait seconds. Now this is the snow depth result that we have by differencing the two DM. This is like 17 meter. I mean, I don't think we can have a snow depth of that. So 70 meter is pretty high. So what do you think is the issue here? What are we doing wrong? Yeah, exactly. So we did the coordinate reference system transformation, but then this project to match that we did only works for horizontal coordinate reference system. So the vertical datum of the two DEMs are still different. So if we look at the Grand Mesa Sonar DEM using the GDAL SRS info, the datum is WGS84. But ASO, QSI, vertical datum is reference to geoid. So we need to make sure that they are in the same vertical datum. So we can either project the ASO to geoid, or we could project the QSI to WGS84. So here is illustrations of the geoidal datum and ellipsoid, and the separation between the ellipsoid and the geoid, which is the ellipsoidal, I think that's geoidal eyes. Yeah. So For these projections, and I think it took me a couple of days to figure this out, and it's very surprising that up till now, vertical datum transformation is still a big issue in elevation data analysis. But then eventually, I found out that it's quite easy to do with GDAL, just that you need to be careful of what datum files you are using when you are transforming from one reference to another. So here, in the data input folder that we downloaded, I've included two GTS files, which is the file that contains information for transforming from one datum to the next datum, or from WGS to geoid. So then I call GDALWAP command. I specify the source coordinate reference system. This coordinate reference system of ASO. And then the target coordinate reference system is just copy the content coordinate reference system of the QSI, but include the geoid information, which is EGM 96_15, geoid nav 88. So then I specify the input file, and then the output should be saved as SOMA_DEM_geoid 96. This takes a couple of minutes to run. Actually, it takes long. So I will just switch to the rendered notebook to while I run it. And proceed with the render notebook, if you don't mind. Okay, so after doing the coordinate vertical datum transformation, then we read the transform SOMA_DEM, and then we do the differencing again. So we project to match here and do the differencing again, and now plot the snow depth. So we see now that the values we get now make sense now. So just be careful when you are using elevation data from different sources. Be sure that they are in the same vertical datum and same resolution and all that. I'd like to add a few notes about vertical datum transformation. So GDAL builds upon PROJ to perform the vertical datum transformation. When you install GDAL, the GTX file that you need for most of the transformation are included in the necessary folder. But there are some transformation that requires larger files. So you have to download those ones and add them to the folder. You can download you can check all the necessary, all the available GTF files here. This is for WGS 2008, 96, USA geoid, and just find out which files you need for the transformation. And another thing is that just look at the documentation, the GPROJ documentation about where the pre-ROG directory is for the installation that you, depending on the operating system, it will be on different folder. Another issues with elevation differencing is co-registration issues. So if the two DMs are not properly co-registered, even when they are in the same vertical datum, you might have some errors of 50 centimeter or thereabout. Lastly, I want to talk about the available LiDAR data, and most of them are available on NSIDC, like this 2013 to 2019 ESO data, and some are available in SnowEx data. But for the ones that I've been working with or working on in the past month, we have submitted the data to NSIDC, but they have not been approved yet. Well, if for the purpose of this Hack Week, or maybe other project that you are doing, you could find the download link here for the 2020 QSI data and the 2021 QSI data for some selected sites. They are 0.5 meter resolution LiDAR data. And we have derived the vegetation height is inside the directory, the snow depth is there, and there's also intensity images. I couldn't hide the point cloud because it's really a lot of data that you might not really need. Yeah, so yeah, this is the map of where we have LiDAR data for 2020 and 2021 over Idaho, Utah, and Colorado. Yes, yeah, that's all from my side. Thank you. I'll take questions.
Wonderful tutorial, Naheem. And Naheem's been working really hard to get these LiDAR data sets ready for use for this Hack Week. Just a reminder that, this is data that's provided prior to being at NSIDC. So if you're going to publish with it, please wait until it's at NSIDC so that you can rerun all of your analysis from the published data set is what we're urging people to do. But you have access to everything that was flown for SnowEx now. Any questions for Naheem? Yeah.
Yeah, so the QSI data that I'm working on was acquired in 2020 and 2021. I think HP and other collaborators contracted the LiDAR survey out to QSI, and it's over some selected sites. I really don't know much about the data acquisition because I was not even there when the data was acquired, but I just work with the point cloud and all that. But I mean, HP is going to give more information about QSI project.
Yeah, so when we were setting up the LiDAR contract for SnowEx 2020 and 2021, it was in 2019, and it was right when ASO was transitioning out of JPL into a private company, and they weren't in a position to bid on the LiDAR acquisition. So we just contracted directly with Quantum Spatial Incorporated, and that is actually the company that does a lot of the flights for ASO. So the main difference is just we had them fly much higher point density than ASO would, and they did a pretty extensive ground control, which ASO normally doesn't do. The ASO is also going to be taking these data sets and producing their products. So snow depth